Okay, now the floor is yours.
Okay. Hi everyone for having me. Today I'd like to talk to you about the topic that is now on screen. The title of the talk is actually encrypted, so let's apply the encryption key. Okay, this is Mastering Cryptography Fundamental with Node's Crypto Module. So this is a bit of a mouthful, so let's break it down and understand it exactly. So when we talk about cryptography, this is the study of, or the science of, techniques of secret writing or secret communication. And as you can imagine, this plays a major role today in computing and the internet, because we want our correspondence to always be secure. Now, luckily, Node.js has a built-in library for doing cryptography with different cryptographic algorithms. It is actually one of the built-in libraries, just like FS, so you can start using it right away without the need to install anything. And it is actually a JavaScript wrapper around OpenSSL, which is the widely used and a trustworthy open source library for handling cryptography. So it's a wrapper on top of that. Now, like I mentioned, it's one of the built-in modules. So this means that it also has documentation in the Node.js official website. So you can go there and learn about what are the different algorithms and APIs that it offers. But in my personal experience, I saw that, for me at least, it's not the best place to get started, because it kind of already assumes that you're pretty familiar with cryptography. You know which algorithm is used in which use case, and then you just need to look up like exactly what is the signature of this algorithm in JavaScript. But if you're more like me and you're new and you're thinking like, okay, what are even the options, what are the concepts, then it's not the best place to get started. Now, luckily, you have other resources in other places. You have books, you have other online courses. So you can go to other places, kind of learn the basics, the concepts of cryptography in theory. And then if you want to use them in JavaScript and Node.js, you can come back here and learn about the API, the specific APIs. Now, this is what I want in this talk to give you a shortcut through. I want us to cover the major concepts in cryptography. What are the solutions we have, where each solution still falls short, and we need to add another solution on top of it. But for each one, I want us to see how it's actually made available in the crypto module and JavaScript, so that you can actually go and build something real with it pretty quickly. So let's get started with that. My name is Yonatan Mevorach. I'm a web developer from Wix.com. I wish I could be there today with you, but unfortunately I couldn't. This is where you can find me online. So the first topic that we're going to cover is that of encryption. This is the main thing that we think of when we talk about cryptography. This is where we have two parties, let's say Alice and Bob, and they want to exchange information between them. And they want to do so in a way that only they will be able to understand the secret message that they send. They are going to be talking over an insecure channel, let's say the internet, where our messages are relayed through lots of other computers. So they're going to have to assume that somewhere on the network or on the channel, there is an attacker, someone like Eve, who is going to be able to read the data that they send across. So this is why they will use encryption. When the message is encrypted, even if the attacker in the middle can read the message, they don't understand the meaning behind the message. For this first type of encryption that we're going to show, it's going to rely on something that both Alice and Bob need to agree on and both have a copy of, which is a piece of data that we call the key. And we're going to talk more later about exactly how do they set the value of the key and how do they transmit the key between them. But for now, let's just say that it's something that they both set and they both have a copy of. Now, what the key enables them to do is to perform the encryption. This is a simplified model. We're going to see how it works more, the real-world process in a minute. But by combining the key with the plain text, which is the original message that Alice wants to send, Alice gets the ciphertext, which is the encrypted message. So let's say if she wants to send the message JSConf JP, she applies the encryption function, passing in the key as well. She gets back this ciphertext, which looks like random data. She can send this over the public channel, and then if Eve sees this, then nothing bad happens because she doesn't understand the real meaning. And then Bob, using his same copy of the key, can apply the decryption and read the original message. So what are the real-world concerns that we need to think about when we do this process today? So the first thing to consider is the encryption algorithm. We have more than one encryption algorithm. All of these work by doing a set of transformations and substitutions on the original message to get the ciphertext, and then to get back the plain text during the decryption, you perform the reverse operations. But we have lots of different algorithms, so you need to choose which one to use. Now, this is actually the first piece of code from the crypto module that I want to show you today. This is the getCiphers function, and this one is very simple. You call it with no parameters, and it returns a list of all of the algorithmic, all the cryptographic algorithms that are available on your machine. So let's say that Alice and Bob will use a standard called Advanced Encryption Standard. And as the name suggests, this is a standard that is widely used and also considered advanced and secure enough for modern use cases. Specifically, they're going to use, let's say, AES 256. This stands for the size in bits of the key that they will use for the encryption and decryption. And they're going to use CBC mode. This stands for cipher block chaining. This is a mode of encryption where the message is split into these chunks or blocks, and each chunk is encrypted on its own. When you're working in this mode, you need to, in order to compute the very first block, you need to pass something which we call an initialization vector, or IV for short. So let's talk about how the IV makes our encryption more secure and what value do we set as the IV. So this is more like how the encryption will really work. Again, to do the encryption, she has the key and the plain text, but now she also must apply the IV. And the value which is used as the IV is a random value, or as close to possible as truly random, if possible. So it means that even if every morning Alice sends Bob the same message, hello, using the same key, she will use a different IV every time. And this deterministic function, the encryption function, given the same input, it will always return the same output, now will return, because the input is different every time, a different output every time. So even given the same message, the output will be different. And this is what is helping the IV make our correspondence more secure, because it eliminates things that are repeating, that given the same original message, it will return the same ciphertext. And by introducing this randomness, we are making it harder for Eve to find these patterns and break the encryption. And therefore, this is how the process looks like now. This means that in order to do the encryption, to perform the decryption, Alice must send Bob the IV that is used. It doesn't have to be kept secret. Bob will need to use the same IV value to do the decryption. And like I mentioned before, they need to both use the same algorithm, because you can't use one algorithm for encryption and a different algorithm for decryption. And then Bob can do the decryption and read the original message. So now let's see how this is done in code. This is Alice's encryption code. So she will take the algorithm that we chose. She will take the message that she wants to send. She will convert it into a buffer. We don't work with strings. We only work with buffers of byte data with the crypto module. She can call the random bytes function available on the crypto module to get the random IV value. She will load the key into memory. We'll talk later more about how the key is set. And then she's ready to create the cipher object using the create cipher IV function. Then to compute the ciphertext, she passes the plain text and gets back the ciphertext. She has the option of calling this update function on the cipher many times. If the original plain text is composed in parts, then you can also compose step-by-step the ciphertext. But if the message is short, you only need to call this once. And now let's take a look at Bob's decryption code. He gets the IV, the ciphertext, and the algorithm from Alice. He loads the key into memory, same key, same value. Now he's calling a very similar looking API, but this is create decipher IV for doing the decryption. And now, given the ciphertext, he is getting the plain text. And only he, because he has the same value of the key used for encryption, can now read the original message again. All right, so this is the major thing that we want to accomplish with cryptography, this idea of encryption and decryption. But so far, we kept it pretty vague about what is this key, how do we set its value, etc. So let's talk about that next. Alice and Bob might be tempted to use a simple password that they both can easily remember as the key itself. But this will be a mistake. If we have a key size of 256 bits, this means that there's a huge number of possible key combinations. So if Eve wants to try to guess the key, she would have to look through and iterate over all those options. But if Eve, the attacker, can assume that Alice and Bob are using a short, memorable password, then she has to try a much narrower, a much smaller set of potential keys. This is why we don't want to use a short, human, memorable password as the key. But what can we do if we still want to use a human, memorable password as the basis of our key? For this, we can use something which we call the key derivation function, or KDF. This is a function that will take as input a human memorable password and will return a stronger, longer key. Now, the interesting thing about these type of functions is they're very similar to hash functions, which you might be familiar from doing file integrity checksums. But unlike those functions and unlike most functions, KDFs are designed to be slow. They're slow on purpose. They're meant to take up a lot of compute power and a lot of memory sometimes as well. This is because we want it to be very difficult for Eve, the attacker, who is trying to loop through known passwords. We want it to be so that on every iteration, on every attempt, she will have to execute this KDF, and for that to be very expensive and take a long time for Eve on every iteration. So this is why these are strange functions that are actually made to be slow. Now, if you think about this, we still have a problem here with this approach where we only supply the passwords as the input, because this is a deterministic function. So what Eve, the attacker, can do is she can go online and find a list of common passwords, and then find a pre-computed list where somebody already ran those original passwords through a well-known KDF, and then she can just use the values on the right as the key value. She doesn't really have to perform the execution, the running of the KDF. And therefore, the benefit, the security benefit that we get from the KDF is nothing. It's just making our encryption more complex, and it's giving us no added value. This is why KDFs actually take a second parameter, which we call the salt. And this salt is, again, a random value. And it is combined with the human memorable password. This means that even if Eve, the attacker, learns what our salt is, then if she's trying to loop through common passwords, she now has to combine them with the salt that she discovered, and it means that she still has to run and execute the KDF. And this will make her cracking attempts much slower and ineffective. And this is why this helps make our KDF secure. So let's see how this is done in Node.js. We have a KDF that's called script, secure script, baked into the crypto module. You take the original password, you generate a random value as the salt, you pass it to script, and it will return a key. All right. We have two other KDFs in the crypto module, HKDF and PBKDF2, which you can go and read more about. So as we saw by now, being able to generate random values is very important to being able to work with cryptography. So the first rule of generating randomness in JavaScript is don't be tempted to use the familiar math.random for doing cryptography. As is stated in the MDN documentation, this function is not considered cryptographically secure, which means an attacker can either guess what this will return on your machine, or they can do something to your machine to choose a number that the attacker planted there. So don't use that. Luckily, inside the crypto module, we have other methods of generating random data. All of these functions are asynchronous, but they don't work with promises. So if you want to work with promises, you need to call util.promisify on them. So let's go over them. The first one, as we saw before, random bytes. You give it the number of bytes that you want to get, and it returns a new buffer of that size with random data. You have a random fill, which takes an existing buffer and either fills all of it or a subset of it with random data. You have random int, which given a range, minimum and maximum, returns an integer in that range. And you have random UUID. All right. So if you think about what we saw so far, we have a way of doing encryption. We have a way of generating a strong key. But the weak link here becomes the fact that Alice and Bob need to use the same key, which means that somehow they need to agree on and share with each other which key they're going to use. Now, if Alice and Bob represent computers and are talking over computer networks, they don't have the luxury of meeting offline and like whispering in each other's ear what the key is. They need to share the key that they chose over the network, but they can't use the network because this is where the attackers are. So as you can imagine, this is a big problem. And Alice thought long and hard about this problem, and so did I. It confused us quite a lot. And this was known as the key distribution problem. And it was a major problem in cryptography. Luckily, it was solved in the 1970s by a group of researchers, and they published the algorithm that now bears their name. This is the RSA. And we're going to see how this process that they came up with basically solves the key distribution problem in a completely other way. And the basis of their solution is that they will use, or Alice and Bob will use, a different key for encryption and a different key for decryption. So in this process, which we'll review now, Bob needs to first create what we call a key pair, two keys, a private key and a public key. Sorry. And then he can share the public key with the world. It's totally fine if everybody knows this key value. And then if someone like Alice wants to send him a message, she can take his public key and the plaintext and use it to create the ciphertext to do the encryption. She sends him the ciphertext, and he is the only person in the world that, using his private key, can decrypt the message that was encrypted with his public key. So this is how it works. Let's see how this is done in Node.js. First, to create the key pair, Bob can call the generate key pair function. Now he will have the two keys in memory, and for each one he can call the export function on it to save this to file using the standard way of serializing these keys, the formats. And he will keep the private key private and send the public key to whoever he wants. Now to perform the encryption, Alice will read Bob's public key into memory using the public key file. She will take the original message, and she can call the public encrypt function from the crypto module and then she will need to pass the public key, the plain text, and a constant value that she needs to set called which padding configuration to use. And then to perform the decryption, Bob will take the ciphertext, he will read into memory his private key, and then he will be able to call private decrypt, passing in the same values and the ciphertext, and then he will be able to read the original message. So with this idea of different keys for encryption and decryption, the key distribution problem is solved. We have another notable mention. Also in the 1970s, a different group of researchers published a different solution to the key distribution problem. This is known as the Diffie-Hellman key exchange, and it is available in the crypto module, as well as another, I would say, more popular used today algorithm by the same group of researchers. This is elliptical curve Diffie-Hellman, also available in the crypto module. So this really caught on and became popular. But if you think about it, in this world where everybody can send encrypted messages to one another and verify them or decrypt them with the public key, the issue becomes, how do I know that the message really came from a specific person? So let's give an example. Let's say that Alice is one of the organizers of JSConf, Japan, and she wants to send Bob a message saying that he can prove that he got a message from her, one of the organizers, that he can go into the conference hall on the day of the conference. The only reason that somebody would let him in is if Bob can verify that the message really came from Alice. So let's see the process they can use to do that. This is where we talk about signing and verifying messages with cryptography. So what Alice can do is she can take her message. It doesn't have to be an encrypted message. And she takes her private key. And using that private key, she can create a signature value. This will look like just a random value, like a hash output or something, of the original message. And then she can send that message and signature to Bob. Her public key is known to Bob and to everyone else. And then Bob, to prove that the message really came from Alice, he can take her public key and perform this cryptographic verification on the signature and the message. This will only return that the output is valid if it actually came from Alice, or rather I would say only someone with access to Alice's private key can create such a signature that when combined with Alice's public key makes it so the math lines up and this returns that it is indeed valid. Let's see how this is done in node.js. So to perform the signing, Alice will read her private key into memory. She will take the message that she wants to sign, and she will use crypto.sign to create the message itself, passing in the hash function to use as part of the signing process, the message and the private key. Then Bob, to verify the message, will use Alice's public key, and he will call crypto.verify, passing in the same values and also the signature, and this will only return true again if the keys and the math all line up. We have another method of doing this authenticating and verifying in the crypto module. This is called create HMAC, hash-based message authentication code. And so I encourage you to read more about that. This is more in the world of when you're not using asymmetrical keys. So again, Alice and myself, we're happy to see what we've now learned about signing and verifying, but we're not convinced yet. Because if you think about it, it doesn't really prove that the message came from Alice if we verified it using her public key. It just means that it's someone with a private key and a published public key that says this is Alice's public key. But how can we know for sure that a certain public key really belongs to a certain entity or a certain person? This is where we use public key certificates to establish ownership of a particular public key. So let's talk about certificates in general, not cryptographic digital certificates, but just certificates in general. So here's an example of a certificate. This is a certificate given to me by the creator of Git, Linus Torvalds, for being the absolute best at remembering Git commands without ever needing to consult documentation. And I can prove to you that it's real because it has a signature right here. Okay? Digital certificates are similar. They are presented to a certain subject by a certain issuer, and they have some claim that they want to establish to that entity and a signature. Okay, I hope you figured out by now this certificate is not real, it's fake. But in cryptographic certificates, we have the luxury of being able to verify that the certificate is real using the cryptographic signature. So let's see how this is done. Alice and Bob want to communicate. So in order to do that and to trust each other, they will both have to find a different third party that they both trust. So let's say that they will use Carol. As you can see by the close, of course, Carol is Bob's sister, and she's also a friend of Alice. Now, Bob already trusts Carol, so Alice will ask Carol to create a certificate for her saying that Carol knows Alice and therefore Bob can trust her. Basically, Alice wants to prove that her public key really belongs to her. So she will take the public key and some metadata about herself, her name and her country, and she will create a certificate signing request to Carol. Carol will take this data, which is called the TBS, to be signed, part of the certificate, the draft of the certificate, and if she wants to help Alice, she will sign it with her private key and create a cryptographic signature. And then Alice will take all this data along with the new signature and create her certificate. Now Bob can, in order to make sure that the certificate is legitimate, he will verify the signature. He says, okay, this is signed by Carol, who I trust, so I will take Carol's public key. And using the same process I showed before, I will make sure that the signature is valid using Carol's public key. And if so, then I know that I can now trust Alice's public key. So let's see how this is done in node.js. We have a class called X509 certificate. You can read the certificate file into memory. This is X509 is the name of the standard for these public key certificates. You can read the metadata on the certificate, like who is it for, who is the subject, Carol, who is the issue, the subject is Alice. The issuer is Carol. We can check the range, until when is the certificate considered valid. And to actually perform the verification, Bob can read Carol's certificate, which has Carol's public key, and he can verify Alice's certificate using Carol's public key. And if this returns true, he can start verifying messages from Alice using her public key because it is really Alice's public key. Now you might think by now, okay, but how can Bob trust Carol and know that this public key really belongs to her? Well, how do you trust your sister? Of course, you trust your sister because your mom told you so. So this is Doris. And what I'm trying to illustrate here is that we have this certificate chain. Okay? So if you go to any browser, like for example to the Node.js website, and you look up the certificate for Node.js website, you will see this certificate chain where your browser trusts the certificate of the Node.js website because it trusts a different certificate, because it trusts a different certificate, and at the very top, there's a root level certificate that your browser trusts because it is baked into your operating system or browser. This is like your mom certificate. So now we've kind of gone through all this process and we can start communicating securely. To wrap up, I created this website with all the code samples today that you can run. So I encourage you, if you're interested, to do that. This is the Wix website, of course. And also, look, we've covered all these topics, so this is quite a lot. So I now consider you a cryptographic expert. So again, in this website, if you go and you enter your name or nickname, it doesn't have to be a real name, and you click on generate your certificate, you will get back a certificate like this with your name. And to prove that it's real, it has a cryptographic signature which you can verify with a public key. So I encourage you to do that, and thank you very much for having me.